Okay, let's go ahead and get started. I'm Charlie Smith, Executive Director of the Energy Systems Integration Group. I want to welcome you to our monthly webinar series and give you a little bit of background on eSig. For those of you not familiar with eSig, we're a membership-based nonprofit organization providing our members with objective information and resources for renewable energy and energy systems integration decisions. We do this through our workshops, tutorials, webinars, blogs, working groups, and technical resource materials. Our most recent activity was our annual Forecasting and Markets Workshop, which was held online during the month of June due to the coronavirus. Our webinar sessions are open to everyone, so please feel free to register anytime on the eSig website. Our workshops deal with a full range of issues associated with integrating wind, solar, and storage into electric, gas, and thermal systems. They also deal with the coupling to energy-consuming infrastructures, especially electric transportation, buildings, and industry. eSig is a very unique organization, and I don't think you'll find anything quite like it anywhere else in the world. If you're new to eSig, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. You can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, and Twitter. Okay, just a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. And for the Q&A, we've been trying something a little bit different lately. We've moved to the Slido platform at slido.com, and we're asking you to use Slido to ask your questions. You'll not be able to ask your questions through WebEx. You should go to slido.com on your device and enter today's date, July 22, as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions to allow you to cast a vote to help prioritize the questions submitted. We plan to wrap it up at the top of the hour, and an email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions using Slido. Okay, so today our webinar is on the topic of System Black Start with DER. Based on registrations, it looks like this is another quite popular topic. The webinar will feature Peter Chandler with the National Grid Electricity System Operator in Great Britain. Peter has worked for National Grid System Operations for 27 years and is currently leading the Distributed ReStart project. He manages all aspects of the project, including the budget of £12 million, project implementation, and reporting to the regulator and stakeholders. Peter is a man of many talents and has held many roles at National Grid, including post-event review, operational planning, emergency planning, including Black Start, business continuity management, and control room operations, where he was responsible for real-time balancing and management of Great Britain's power system. He has successfully delivered a number of high-profile projects, including the legal separation of the electricity system operator from the wider National Grid business, new Black Start services, and drafting the Emergency and Restoration European Network Code. I feel very fortunate to have Pete here with us today, as he has a wealth of practical knowledge and experience to share with us. I greatly value his contributions to the industry, and I look forward to what he has to say. On today's webinar, we'll be hearing about Black Start, which is the procedure used to restore power in the event of a severe disturbance resulting in the loss of power to a large region of the electric system. The National Grid Electricity System Operator of Great Britain has undertaken a new project called Distributed ReStart, which will demonstrate a world-first Black Start service through the coordinated operation of distributed energy resources. The Distributed ReStart project, a 3-year effort, has reached its halfway point. Removing the dependence on large fossil fuel generators for Black Start will help reduce costs and achieve a net zero carbon grid in Great Britain by 2025. It will also make possible the UK government's net zero carbon target for 2050. Flexible demand companies and DER would benefit from revenue for the provision of Black Start services. The webinar will provide an overview and status report on the project. Okay, just a short reminder once again to use Slido at slido.com with the event code of today's date, July 22, to ask your questions. Now, without any further ado, let's go ahead and get started. Pete, I'll now turn it over to you.
Thank you very much, Charlie. Thank you for the introduction. Hello, everybody. So as Charlie says, my name is Peter Chandler, and I'm here to talk to you a little bit about project I'm running, Distributed ReStart. Hopefully you'll find this useful, but feel free to fire in your questions via slido.com as we go through. So, Black Start. Some of you might already know what Black Start is. Charlie gave a little bit of an introduction there. So Black Start essentially is a technical recovery from a regional or national blackout. So the term Black Start is kind of synonymous with sort of blackout, but it's actually the recovery phase. So Black Start's about recovery. In the UK, we've been very fortunate. We've never had a Black Start, a regional or a national Black Start event happened. We've had a sort of small regional event back in 1987 when we had sort of high winds, which took out the southwest corner of England. But we've never had a national sort of blackout event, but they do happen around the world. We've had a number in the last few years, Argentina and India and other places like that. I think the US as well in 2003, New York. So they do happen, but they are a low probability event, but very high impact event. So it's really essential that every country has its own sort of technical recovery plans to cater for sort of national, regional sort of blackouts. So what is a kind of a technical recovery procedure? What does it look like? So from certainly sort of GB perspective, from Great Britain's perspective, it's about current plans are about restoring the transmission system. So I'll take you through a little bit about the energy supply industry here in Great Britain in a second. But essentially, in Great Britain, this is about restoring the transmission system, utilising sort of large transmission-connected power stations. Traditionally, these have been fossil fueled. We've got a number of sort of coal-fired power stations that have Black Start capability. All of those coal-fired power stations will be closing. They've either closed or they'll be closing as we head toward 2025 as part of the sort of decarbonisation of electricity supplies. So moving away from traditional large power stations, fossil fuel-powered power stations, and moving to a more renewable landscape. A lot more renewable sources of generation connecting at transmission level and at distribution level. And that's only accelerating as we sort of progress into the sort of next part of this sort of decade. So just promised you a little bit of a précis about the GB electricity supply industry. So over here in Great Britain, it's a fully privatised industry currently. I think it was privatised back in the 1990s. 1990 was the big vesting period where the industry moved over from sort of public ownership to private ownership. So you've got a lot of different stakeholders involved. You've got the kind of network provider companies at transmission level. We call them the transmission operators, the TOs. We've got the generators themselves. So lots of different generator companies, quite a wide and diverse variety of generator companies these days. We've got the distribution companies. We call them DNOs, distributed network operator companies. So they're all kind of privately owned. And then there's ourselves, National Grid, electricity system operator. We are charged with the overall system operator responsibilities, mainly for the transmission system for Great Britain. So that's kind of how it's kind of structured in Britain at the minute. We're heavily regulated, so it's a heavily regulated industry at the moment, so heavily sort of regulated. And Ofgem, the Office of gas and electricity markets are the sort of regulator in charge of sort of regulating the whole sort of GB. So that's a little bit of an intro about the kind of structure of the sort of power industry in Great Britain. So National Grid Electricity System Operator, we sit right at the heart of system operations, and even more so now right at the heart of the transition to decentralisation and decarbonisation of energy. So as Charlie mentioned, we've got some big sort of incentives pushing towards being able to operate the power system with zero carbon by 2025. So that's a massively challenging ambition that we've set ourselves. And this project, which I'll talk to you in a second, fits directly into that kind of ambition. So going back to Black Start, so traditionally this has been about restoring transmission system supplies, so having contracts in place between the electricity system operator and sort of individual generator companies, and those contracts will be bilateral, historically, bilateral contracts. And then we'd involve those generators in what we call a local joint restoration plan. So effectively, this is a small power island. This is a part of the transmission network. This is a distribution network company providing the source of demand, the generator itself providing the source of sort of Black Start power, and the electricity system operator coordinate it all. And the way it's traditionally done is that the ESO would instruct a power island to start, and effectively it would create these small power islands across the country, and then it would start to grow those power islands and then stitch them together, synchronize them together to create a synchronized skeleton network. So that's how it's done. That's how it's been done for the last 40, 50 years back in GB. So moving on. So why Distributed ReStart? So this is the name we've given to our project. So this is about a bottom-up approach for Black Start restoration services from the distribution networks up to transmission level. So rather than a top-down approach, which is our kind of historic approach for Black Start, this is a bottom-up approach for Black Start, utilising DER, distributed energy resources, connected to the distribution system. So we've been set this challenge, and the objectives of this project are to reduce costs to consumers by creating competition, by introducing more players, more participants into the market, increase competition, drive down those costs for consumers. This is also about the transition to renewable energy and decarbonisation, so a shift away from our traditional carbon fueled power stations we hold in readiness for Black Start, moving towards more renewable sources. And also we think we can accelerate restoration timescales at a regional level by introducing this kind of concept of distributed energy resources doing sort of Black Start. I'll come back to that in a second about accelerating timescales, because there's an important point on that. So there's a whole bunch of things we've got to kind of solve here. There's all the technical challenges, all the sort of network challenges. I'll talk to you a little bit more about that in a second. There's the challenges around the generator itself. There's the communication side as well. How do all of these parties talk to each other on the day? Obviously there's a requirement here for resilient sort of telecommunications. Is there a need for systems, sort of smart systems to play a part here? Automation. There's a whole bunch of things that we are trying to solve. Also, we're looking at the kind of commercial framework about how we can incentivize and encourage new participants to take part in a kind of a new Black Start from DER service. So a little bit about the project itself. So Distributed ReStart, this is a 3-year project. This is an innovation project. So over here in Britain, we've got this concept of called network innovation competition. So the regulator allows a certain amount of public funding for energy companies to go away and do innovation projects, to come up with sort of new ways of doing things. So as Charlie mentioned, this is just under sort of £12 million worth of public funding set aside for this project. We started this project back in 2019. So it's been going for roughly 18 months. So we're roughly about halfway through. So we're due to conclude by 2022, end of March 2022. There's 3 companies associated with this innovation project. There's National Grid ESO, the Electricity System Operator, which I represent. We are the kind of the Black Start experts at the moment. So at the moment, the ESO is accountable for procuring and delivering and instructing Black Start services on the day. So we are kind of the Black Start experts, if you like. There's Scottish Power Energy Networks. So they're a distribution company. They've got a wide variety of and diversity of DER, distributed energy resources, within their kind of distribution patch. Lots of different network challenges as well. So they are one of a number of distribution companies, and they were chosen to sort of partner us as the kind of network experts, distribution network experts. The third company in this partnership is a consultancy company called TNEI, and they're based out of Glasgow, Manchester, and their primary function and expertise is around power system modelling. So power system studies, the sort of detailed sort of study work that we need to inform the project of kind of sort of restoration routes and needs and options. So 3 partner companies. This is as I say, this is a network innovation project. There's a whole bunch of sort of governance around that. I won't go into that detail, but mainly we are structured along the lines of 3 main work streams. One is a technical work stream. We call it Power Engineering Trials. So this is looking at all the technical challenges around Black Start from DER. A lot of the case studies I'll mention in a little bit, the study work around that. So all the kind of technical challenges, the options around those challenges, and then you sort of propose solutions to overcome those challenges. And you'll see the and trials bit, which is quite interesting. So we hope to do some demonstrations, some actual live trials with 3 live case studies within the Scottish Power Energy Networks distribution area. So that's quite exciting. We hope to sort of kickstart that later on this year and then proceed into next year with sort of further type trials. So that's quite interesting. So last year, 2019, we did some initial case study work. So we created 10 case studies, sort of small mini power islands with a sort of wide variety of challenges at a network level, but also at a generation and demand level as well. So the idea of picking those 10 case studies was to create kind of a generic library of learning so that we can translate that across the whole sort of Great Britain country and sort of roll that out in a sort of nationwide set of learning and solutions. So we did a lot of work on initial building sort of 10 case studies last year, and I'll talk a little bit further on that a bit later. The second work stream, which is worth mentioning, is Organisational Systems and Telecoms. So this is about how we organise ourselves. As I mentioned earlier, the electricity system operator has a primary role at the moment. That they are effectively responsible, the control engineers on the day, if it ever happened, of instructing sort of Black Start services from power stations and then growing those power islands and then stitching them together. So it's very much an ESO-led activity at the moment. Going forward, what will that look like? You know, is there still a need for the electricity system operator to be the primary driver here, or can we delegate some of those restoration responsibilities to the distribution companies? So that's what we're looking at. So that's one of the things we're looking at in this work stream. The other side of this work stream is looking at the system side. So what level of systems might we need to complement the different organisational structures and models? And I mentioned already about telecoms. So any telecoms that we need needs to be resilient. And post-blackout, existing telecoms may not necessarily be that resilient. So there's a lot of work on telecoms as well we're delivering. The third work stream, which is a commercial work stream, this is looking at procurement and compliance. So this is actually designing a commercial framework for Black Start from DER. What services might be required for participants to be incentivized to participate, in a sort of Black Start from DER service, and different ways of procuring that service as well. So I'll talk a little bit about that a bit later on. So three main sort of work streams. And last year, 2019, was very much an optioneering stage of the project. Look at all the sort of different options around the three work streams. So where we are now, 2020, 2021, we're very much in a kind of a design phase, doing some detailed design work on some of those case studies, on some of the sort of system requirements and some of the telecommunication resilience challenges. Also some detailed design work around the commercial frameworks and the procurement as well. So that's where we are at the minute. And as we sort of head towards the latter part of this year, into the sort of autumn and winter period and into early next year, we'll be doing some demonstrations. So I mentioned about live trials. So this is physically doing live trials, doing real Black Start from DER testing, stuff that we've never done before. Also, we'll be doing some road testing of our new processes through some desktop exercises. So we hope to do those desktop exercises next spring. So this will effectively be role-playing the kind of organisational models and also some of the new systems and telecom solutions. So there'll be a whole series of desktop exercises, whole series of live trials, and alongside all of that, a whole detailed piece around commercial design. So this slide pops up a bit later, but I'll come back to it if I may. So technical challenges, lots of different technical challenges, as you can imagine. Black Start from DER. I mean, what we're proposing to do here, Charlie mentioned a world first. I believe what we are proposing to do, we're tackling the technical challenges, the organisational challenges, the need for automation, the impact on resilient telecommunications, the procurement and commercial. So all of that stitched together in a physical project to deliver a real system post-April 2022. As far as I'm aware, this is a world first. This is something this ambitious has never been done before. So I'm quite excited by this. But going back to the technical challenges, we've kind of split that up into three. There's the generation side, or the DER, if you like, the distributed energy resources. So challenges around that, challenges around the demand, and challenges around the kind of networks side of it as well. If you solve all three sets of challenges, then effectively you've solved the problem of Black Start from DER. Just to take you through a few of the challenges. So how do we communicate on the day? I've already touched on the need for resilient telecommunications, and who instructs the generator to start. This is concept of an anchor generator that we've created. Now, an anchor generator is effectively the initial self-starting unit, generating unit, that will provide the voltage reference and be able to regulate frequency. So we've called this an anchor generator. Now, does that have to be synchronous? Traditionally, it does. Could it be asynchronous? That's kind of an interesting question. So we'll come back to that in a bit later on. The DER, the generator, the location of it is key. It has to be located on a part of the network which can be split up, which can be islanded, segregated. It has to be able to deliver frequency response. So a lot of these distributed energy resources are not. It's not normal for them to be in frequency response mode. So to do kind of a power island and a stabilizer power island, they're going to have to be able to do that. They have to regulate voltage. So the way they do regulate voltage is going to need to change compared to what's done currently. There's a challenge around fuel. There needs to be enough fuel for that generator to be running for a number of days, and able to allow the sort of wider network restoration to proceed. And I think stability. So the generator has to be stability, and that's key during the phase of applying the demand in kind of block loading capability. So there's quite a number of challenges there for generation. On the demand side, the flip side, if you like, so block load pickup. So this is the kind of the chunks of demand that a generator has to be able to pick up to load up to a stable load, and that's applied in blocks. So what's that kind of block load capability and you know, the demand? Do we need some sort of flexible demand in order to stabilize that generator? There's this concept called cold load pickup. So this is when you are restoring demand from blackout. You don't necessarily know how much demand you're going to get. It could be up to 1.5 or 2 times what you saw prior to blackout. So this cold load black pickup risk does prevent a big risk to a generator and the stability of that sort of generator. So is there a way to mitigate that? And can you use flexible demand, you know, load bank or a battery or something like that to provide that kind of flexible demand? So we'll come back to that a bit later as well. And then moving on from that is the kind of consumer demand. When is the best time to start restoring consumer demand? And depending on the complexity of all of this, do we need to do fast switching? Do we need to switch in customer feeders and switching in blocks of load, you know, quickly, and how quickly, and how do you do that? So there's a challenge around that. Third set of challenges around the networks. So certainly the GB power system is not designed to be back energized. So back energizing from the 33 kV distribution system up to the 132 kV and up to the 275 and 400 kV supergrid systems. It's not necessarily designed to do that. It's designed to be top down, but rather than bottom up. So what are the challenges around that? There's challenges around protection systems with low short circuit levels. There's challenges around earthing, automation I've already touched on, and the ability to segregate networks I've touched on already. And then the ability to synchronize sort of small power islands as well. So currently we have that ability at transmission level only. How do you synchronize at distribution level? So that's again is another sort of challenge. So lots of challenges. So just moving on, this is a kind of an idea. This is, you think about a small power island. We've called it a distributed restart zone, a DRZ. That's our kind of sort of philosophy, our kind of terminology for this. Think about a small power island and what you need within that small power island in order to stabilize that sort of power island. So you need the initial source of black start capability. As I mentioned, this anchor generator, which I mentioned earlier, the ability to start, create a voltage reference, to stabilize, regulate frequency, and ability to block load. So every sort of DRZ, every sort of power island needs at least one of these anchor generators to do that. We are trying to be technology agnostic. So what I mean by that is traditional synchronous sources of anchor generation may do the job, but we're also looking into the new worlds and the renewable technologies and the converter connected sort of technologies as well. So we are remaining technology agnostic with regard to the sources of DER that are required. Some of these DRZs are not necessarily suitable for providing the kind of oomph, if you like, the energizing power up to transmission level. Ultimately, we are looking at a number of things as a project, and ultimately we are looking to sort of create a DRZ at distribution level, and then ultimately to energize up to sort of transmission level. Some of these DRZs may not necessarily be technically possible to do that, so that's something else to bear in mind. And there's a whole range of automation and smart systems that we might want to include in order to create a sort of small power island and stabilize this power island and grow this power island. So we have, as a project, we've actually commissioned some work looking at designing a control system to do this. And then the sort of stage 2 of that will be to go away and build that control system and then test it in a live environment. That's something else that we plan to do as part of this project. So DRZ, Distributed Restart Zone, that's our kind of terminology for a power island. Some of the sort of technical challenges I've mentioned, we've done a lot of sort of study work, detailed study work. We've done steady state studies, we've done dynamic studies, and we've done sort of electromechanical transient studies. Our sort of TNEI are our kind of modelling experts, so they've been doing a lot of work for us. I mentioned case studies about 10 minutes or so ago. So what we've done, we've created, out of those initial 10 case studies, we've honed that down to 3. So we've got 3 detailed case studies. So 2 of those case studies are in the south of Scotland, and 1 of those case studies is in North Wales. And we've done some sort of detailed design work around those case studies. And part of that detailed design work is a lot of these steady state, dynamic, and EMT studies that we've done. Some of the results we've got back, and we intend to publish these results in a report at the end of this month, which is next week, next Friday. So look out for that. So there's a whole load of sort of findings in there, looking at our kind of 3 main case studies. This is around block load pickup capability. So we've discovered as part of our study work that the block load capability of an anchor generator will vary during the restoration process. So it's not just about the magnitude of the blocks of load that the generator needs to pick up. Obviously, there will be a change in the resultant drop in frequency as a result of different magnitudes of block loads, but also due to sort of non-linear sort of generator governor and control system characteristics. The further you go into that kind of block loading restoration of that generator and loading that generator up, the kind of the drop in frequency becomes more. So, sorry, there's a question that's come through. So as more substation demands are picked up, the capability will effectively reduce, and there'll be ultimately a minimum frequency level. And I think it's 47.5 hertz is the sort of minimum level of sort of frequency that we're operating to here in GB with regard to sort of block loading capability. So the block loading capability will effectively become unacceptable at a level sort of well below the maximum operational limit of that generator. So that's quite an important point. And it does kind of lend itself to the conclusion that in order to restore blocks of load further down into the restoration process, you need more assistance from other DERs within that geographical area, within that DRZ. So that's quite interesting. Just to give you some stats on that, I mean, a typical distributed energy resource that I'm talking about is a generator between about 20 and 50 megawatts. The sort of block load capability for that kind of unit we found is roughly between about 10 and 25% of that kind of generator's active power rating, which equates roughly to about 2 to 12.5 megawatts of block loads, depending on the kind of blocks. and the kind of resolution of those blocks now there's established. I mean, the smallest possible resolution is a 33 to 11 kV distribution feeder to bring on to customer demand. That cold low pickup effect as well I mentioned earlier, so that you could actually see twice the amount of demand you'd expect, load you'd expect on that feeder. So you get this kind of limitation utilizing the initial black start unit, the initial sort of anchor generator. There's a kind of a limitation around block load capability. So you have to be wary of that. And there's definitely a need to get help from adjacent DERs. So that's one point I wanted to make. That's something our studies have uncovered. So another sort of finding, if you like, is around voltage regulation. So obviously there's a big link here to the sort of weak system of a small power island. You know, the short circuit levels, fault levels as we call them over here in Britain, the short circuit levels, the low short circuit levels, and the switching of whether it's switching in block loads, whether it's switching in transformers or switching in circuits. The fact that the system is weak, the short circuit levels are low in a small power island, you will get large sort of voltage deviations. So the anchor generator will effectively regulate the voltage within the power island. But as I said, switching the block loads, you will get this voltage dip. Now, the rule of thumb we've used for our kind of studies, if you like, is the security standards, security and quality of supply standards, which is the operating standards that we apply over here in Great Britain. During a black start event, those security standards wouldn't necessarily apply, but if they were to apply, a voltage drop of 12%, we'd only be allowed to have. And the example we showed you on this slide is actually a real example from one of our case studies. We're looking at about a 20% reduction in volts at the generator terminals. So there's a big issue there around that. So that kind of reactive response, that voltage response that you need to capture the drop in volts and restore it back to sort of nominal, potentially you need additional assistance from other sources of DER within that group, provide you a stronger sort of system. We've done some other work on energization of transformers. What we found is energizing up from 33 kV networks, which is the sort of typical distribution network voltage level that we're looking at here. So energizing up from 33 up to the grid voltage of 132, and then up again up to sort of transmission level, which in GB is 275 and 400 kV. So we've done a bit of analysis around that. And what we found is that energizing transformers is quite onerous. So potentially you could have voltage drops up to 20% at the generator terminals when you are energizing transformers. And a way of mitigating that could be to employ a sort of soft start approach for restoration, starting with a sort of a reduced voltage level to reduce the impact of inrush currents and the impact of magnetizing the transformer. So that is an option that we're looking to pursue, a sort of a soft start approach to minimize the impact on sort of voltage drops and things like that. There's also another thing that we thought about is point-on-wave switching, so that might help you. You've got circuit breakers with point-on-wave switching, that might be able to help you alleviate some of the sort of voltage depression problems here. On the circuit side, circuit energization, so we're testing around circuit energization. Obviously, we've got the reverse problem here of high volts. The sort of no load gain of sort of circuits and the reactive capability of the anchor generator to absorb that kind of reactive sort of charging power to limit the impact on sort of the high voltage side. So ultimately there will be a kind of a limit, if you like, to the kind of the reactive charging capability of a DER. there'll only be a certain sort of length of sort of feeder line or length of sort of network, and that you can actually withstand at a kind of generator DER level. So again, there seems to be a need here for increasing the short circuit levels, reducing the impact on voltage deviations with the input of additional DER support. So that's kind of a big kind of conclusion that we've come to. How am I doing for time? Okay. System earthing is another issue. So over here, typically the distribution networks are earthed at the 33 kV side of the grid transformers, 132 to 33 kV grid transformers. So when you've got a power island established and DRZ established, in this example, grid 1 circuit breaker would be open. So you've lost your earth. The electricity regulations over here, certainly, and I'm sure over in the US as well, but certainly in the UK, the network needs to be connected with earth as near as reasonably practical to the source of voltage. So the solution is to install a switchable earthing device at the anchor generator 33 kV site. So a small earthing device that you can switch in or switch out and to install at that sort of anchor generator site. So that's something else we found. Short circuit levels and protection. So this is interesting as well. So I talked about the kind of charging power of a generator, but also there's the kind of impact of short circuit levels on system protection. Certainly at the transmission voltage levels, 275 and 400 kV, the protections are very fast acting, in the range of about 50 milliseconds for kind of a zone 1 distance scheme. So very fast acting. Less so at 132 and at 132 and 33 kV. But the work that we've done, and this is based on our kind of case study work, we've actually done some study work and actually proved that at least at 33 kV level, the current protections that are installed on the networks should operate correctly. You will need a minimum short circuit level of 50 MVA for them to operate, but assuming you've got a 60 MVA anchor generator within that power island, within that DRZ, then certainly at 33 kV and also at 132 kV, the sort of next voltage level up, that should be sufficient and allow your existing protection systems to function correctly. The problem comes when you go higher up the voltage ladder. When you get to, ultimately we're trying to create a solution that we can energize up to the sort of transmission levels of 275 and 400 kV. Certainly our study work here for this case study proves that with one 60 MVA generator, we can't do that. It's not possible to do that. You need at least 2 of those sort of generators within that power island to give you the minimum fault level in field, short circuit level in field of 100 MVA to energize up to 275 kV. Up to 400 kV, again, it goes up again. The minimum sort of short circuit level that we proved through our studies is sort of 250 MVA. So the conclusions basically lend us to think about, yes, we can utilize the sort of bottom-up approach from 33 up to 132 kV networks and have the protection systems that were in place before the blackout should function. But once you start going up to transmission level, you'll need either to increase the short circuit levels by integrating more generation into that power island, or have some way of reducing the protection settings. Now, I know modern protection schemes have a weak network kind of capability, and some of them can be remotely instructed from the sort of the distribution network control centers. So that's again a key finding for us. It does complicate our kind of overall solution, but a key finding. Before I move on to the next slide, I haven't got a slide on this, but I'm sure you'd be interested. We've done a bit of research and work on converter connected DER as well. So this is so looking at the kind of grid following converter technologies that are out there. This is traditional wind farms, solar farms, vehicles to grid, battery energy storage. These kind of technologies employ grid following converter connected technologies. So this essentially needs a voltage reference to latch onto. So we've done a little bit of research on that. There are limitations we've identified around that, mainly around the control systems, the phase lock loop sort of control loops, control systems associated with a weak network. You can have sort of erratic voltage deviations, as you know, and these phase lock loops don't behave particularly well, and then can result in the generator tripping. There are mitigations for this. You know, the phase lock loop system can be modified for a weak grid network type of operation. Another mitigation is to increase the sort of short circuit level within the sort of power island group to sort of stabilize that phase lock loop. So that's kind of one angle, the phase lock loop. Also inertia as well. Synchronous generation provides inertia, which helps with frequency regulation, limits the sort of impact on sort of frequency excursions. This kind of technology, asynchronous renewable generation, basically relying on grid following converter technologies, is asynchronous. So it wouldn't provide you that kind of levels of inertia. It is possible to create the concept of synthetic inertia. This is a bit of a delayed response to frequency deviation. So that has some value, but limited value. So we're doing a bit more research work on that, but we're also doing a piece of work on grid forming converter technologies as well. So grid forming is this is the ability to self-start and generate your own voltage signal and regulate frequency, effectively doing everything a synchronous generator can do. And there are converter technologies out there that can do this. So we've just commissioned a bunch of studies from Strathclyde University and from Iberdrola in the Middle East to do some work for us on this. And we'll be publishing our results later on in the year on that. So just conscious of time, sorry I'm overrunning a little bit. There are a number of sort of network restoration options that we've been looking at and studying, all of which we think need some level of automation. So we've created this kind of the smart system called a DRZ controller. As I said earlier, we're designing what that will look like, and we've got some companies doing some work for us on that, and hopefully we'll get to a build stage later on this year and into early next year. So a whole bunch of net restoration options. First option we've been looking at is effectively establishing the small power island at distribution level from the 33 kV system, utilizing an anchor generator, and then and then block loading it up to a stable load. The second option around that is sort of growing that power island and then waiting for a voltage signal from the sort of transmission network, and then synchronizing with that sort of energized transmission system. Third option we've looked at and done some study work on is expanding that power island into another sort of grid supply point area, utilizing the generation and topping up the sort of generation and demand within that power island to grow the overall power island. These are all kind of evolutions of a theme. This is about creating two smaller power islands and then synchronizing them, utilizing the interconnector between those at 33 kV level. Another option. This option 5 is about energising up from our initial 33 kV power island up to the grid voltage at 132, energising across to the adjacent substation, grid substation at 132 kV, and then down into the sort of 33 kV network. So that's very much sort of going up and down again. So that's equally applicable. So there's an option R6 as well that we've been looking at, is energising up from 33 up to 132, which is the sort of grid system voltage levels, picking up a generator, energising the supplies to that generator at 132 kV to assist with the overall sort of system strength and voltage regulation, which allows us to energise up to the sort of main 400 kV or 27 kV sort of transmission voltage levels. So there's a number of restoration options we've been looking at, studying, depending on the sort of network configurations. Some of them or all of them will apply, or some of them won't apply. So just moving on to organisational roles. So we've got a work stream looking at this, looking at the how we organise ourselves on the day, who instructs Black Start, who's accountable for Black Start, where does the accountabilities lie. So we feel that there's still a need for the ESO to provide some sort of national overview and integrate the kind of transmission Black Start options to start those, as well as start the distribution Black Start options. So you end up with like a joined up top-down, bottom-up approach, integrate kind of overall national strategy for Black Start. So the way I see this is going, this is not finalised, but the way I see this is going, there'll still be a need for the ESO to be the overall overseeing party, but the responsibilities around distribution restoration will be devolved effectively, or delegated rather, shall I say, down to the distribution companies to provide restoration within their own distribution networks. So that's something that we're working with the ENA Open Networks projects here in Great Britain, looking at the sort of ways that we can transition from a sort of a passive distribution network operator company to more of an active system operator role. So I've only got a few more slides left. Apologies for sort of going on a bit, but telecoms as well. So there's a need here for fully resilient, end-to-end resilient telecommunications. Currently at transmission level, we have that. We've got a privately owned fibre optics telecom system that links all the players that would be party to a Black Start restoration plan. At distribution level, you won't have that. So we're looking at things like fibre, extending sort of existing fibre networks, satellite phones, microwave technology, private radio, public mobile services, 4G, 5G. So we're looking at integrating all of those sort of capabilities into the kind of existing telecom systems that the distribution companies currently have. So what we found is that no one size fits all, unfortunately. So there will be sort of bespoke solutions to each sort of distribution company. And we will need automation and cyber security as part of what we're looking at. So commercial design work as well. So how do we go away and procure service Black Start from DER services? So there's kind of three options for this. There's having one main lead party would be responsible for providing all of the sort of sub-services, the top-up services, if you like. So there's always a need to have an anchor generator. So does the procurement lead party procure to the anchor generator for all of those top-up services, like kind of sustainable megawatt hours, fast frequency control, inertia, short circuit levels, and demand? Or does the anchor generator sit on its own in kind of the middle option, and are all those other sort of top-up services procured individually? So we're looking at both of those. We're also looking at the model on the right-hand side as well, of having the the sort of top-up services are sort of mandated services, part of our kind of industry codes as well. So we're looking at all of those three options for procurement, commercial design and procurement. Briefly, we're looking at different ways of procuring as well. Traditionally, procurement has been through bilateral agreements between the system operator and generators. We've opened that out. We're now doing it slightly differently with regional tenders. As we move forward into the distributed restart area, we're looking at creating other options like e-auctions and having sort of closer to real-time frameworks for people to participate, procure, and services to be procured in. So we are looking at that as well. So just to summarise this slide, so I mentioned it earlier, so we've got some detailed design demonstration work sort of proceeding, and we'll sort of move into sort of next year on that. And lastly, last slide from me, we had a virtual event 2 weeks ago, which was hugely successful. We had 3 mornings, virtual conference event to showcase some of our sort of technical solutions. All of that information is currently available for people to pick up. And that's me.
Okay, Peter, that's quite a whirlwind tour through the world of Black Start with DER. Quite an ambitious project. Really impressive. We've got a lot of questions here. We're not going to be able to ask too many of them, but one that kind of runs through the questions here is really summarized in the first one that rose to the top. Is the lack of grid inertia provided by DERs a concern for Black Start capabilities and stability in an already fragile state? And I think that assumes that, you know, a lot of the DER is rooftop PV or other PV, which is what comes to mind in the U.S. anyway when you say DER. I think well, and your assumption of what is the DER, what does it consist of, I think is related to that.
Yeah, I think we're looking at from about 5 to 50 megawatts of generator capacity. Well, that could be aggregated, of course, but that's the kind of capacity of generation that we've been looking at, about 5 to 50 megawatts, mainly connected at 33 kV. It could be at 132, it could be lower at 11 kV. One of our case studies is actually, the anchor generator is actually at 11 kV, but primarily at 33 kV, which is kind of the primary voltage level for the distribution companies. Okay,
and I guess that would imply generally a larger generator as opposed to an aggregation, or could it be either in your study?
Could be either. Yeah, could be either.
Okay.
Yeah, I mean, solar's interesting. So we've got some large solar farms that we've been liaising with of the order of about 20, 30 megawatts, quite big ones, but certainly domestic PV. From an aggregate perspective, that's kind of an interesting idea. You would need some sort of smart system and aggregation, but it's certainly in scope, yeah.
And for the grid forming requirement, if you had solar, do you see adding that to your code so that would be required going forward, or would that just be an option that may or may not be available?
To be debated, I think. I mean, the mandated route is certainly a route. I'm not sure the mandated route will get much legs over here. You know, it's quite a large sort of market-driven sort of kind of industry. So we're looking mainly towards market solutions. There is options for mandatory service as well. So we've more to come on that, and it'd be interesting to see the results of our study work on the grid forming technologies as well. So there are projects out there that we've been liaising with that have done this. There are sort of factors that have been able to provide this kind of anchor generator capability out there. Okay.
And there's a lot of questions on microgrids. Have you looked at having microgrids sort of available and ready to go and to provide this kind of service, or what's your take on microgrids?
So absolutely. So microgrid is kind of a similar. So our kind of DRZ concept is like a scaled up version of a microgrid, but we're starting from black. A microgrid, as I understand it, is using a smart control system to keep the power island up and running post sort of interruption of sort of power supplies. So absolutely, they are kind of two sides of the same coin, if you like. And we've been liaising with, there's a research project, Resilience as a Service project, which is doing exactly as you mentioned, using a scaled up version of a microgrid as a kind of a resilient way forward to energize on into and create a sort of a faster way to restore supplies. So yes, that is part and parcel of our kind of stakeholder engagement work. We are kind of linking into those sort of projects.
Yeah, very fascinating. Well, we're getting up to the top of the hour, so we're going to have to wrap it up. I hope you'll be amenable to answering some questions and follow up, Peter. I think a lot of very good interest, and for sure we're going to have you back in a year and a half when you finish up the project and see what happened. So,
yeah, no problem. We had about 120 technical questions from our virtual event, and we've answered them and published them. So by all means, send them over. We'll answer those and we'll give it back to you.
Great, thank you. Okay, so everybody, we appreciate your engagement and look forward to seeing you on our next monthly webinar on Tuesday, August 18th at 2 p.m. Webinar will feature Mahesh Mojaria, now with Renewable Energy Plant Solutions, a First Solar spinoff, and Stephen Dalkey, a DOE Fellow in the Solar Energy Innovators Program. They'll be presenting the results of a research project on the topic of the economics of flexible solar operation in electricity markets, and I hope you'll be able to join us once again. Further information on all of the webinars and meetings can be found on our website at www.esig.energy under events and in our newsletters and informational emails, and you're all invited to attend. Peter, once again, I want to thank you for this very timely, informative, really fascinating webinar, and thank you for your interest. We look forward to seeing you again next month for the economics of flexible solar operation on August 18th. And in the meantime, everyone, take care, stay safe. Thanks again for your participation. Bye now.